Find the natural frequency of given system. Mass moment of inertia of the combined disk is I.
Let us understand given system. Two concentric disks with mass moment of inertia is given. So this mass moment of inertia I is mentioned in the question. Now for this inside disk, small m, that is the mass small m, is connected and it is getting displaced in the downward direction through a distance x. Spring with stiffness k is connected to the outer disk. Now we have to find out the natural frequency for this system. We are going to solve this question by using energy method. So we have to find out the kinetic energy as well as potential energy in the system. Now for this mass m, linear displacement small x is there. So there is the translational kinetic energy. So how we can write this Ke translational? So I will write here Ke translational. So we have formula half mv square, that is velocity square. So we can write here velocity in terms of x, that is x dot. So I will write here half m x dot square. Now as this mass m is getting displaced in the downward direction because these two disks are concentric. So here the rotational motion in the disk is taking place. So we have to show here the angular displacement theta for these two disks. So the rotational motion is taking place in these two disks and the combined mass moment of inertia I is given. So how we can write the rotational kinetic energy for this concentric disk? So I will write here Ke rotational, that is half. Now instead of mass m we have to use I, because for the rotational kinetic energy we have to use mass moment of inertia I into theta dot square. So here the angular displacement theta is taking place, so we have to use here theta dot square. Now we will use for this potential energy. So in this system potential energy is due to the energy stored in the spring with stiffness K. Now we will consider as the mass m is getting displaced through a distance x, there is the deflection delta in the spring. So how we can write potential energy? So for potential energy related to spring is half multiplied by stiffness K multiplied by deflection delta square. So these are the three motions are taking place in the system. Now we will observe here the relation in between this x and theta. So how we can find out the relation in between x and theta? Now this mass m is connected to the inside disk. So here, or we can say the smaller disk. So we will consider any point, that is the point P. Now suppose this disk is getting rotated through an angle theta, then here is the new position of the point P, that is P dash. Now when I draw here one perpendicular line from P dash on this line OP, then here is the point of contact, I will say B. Now this B to P dash is also equal to this linear displacement x. So from this triangle OBP dash we can say that x is equal to. Now here O to P dash is given, that is for inside disk radius is small r. So x from this triangle OBP dash, because O to P dash is small r, so I can write here x is equal to small r sin theta. So theta is very small, so sin theta is equal to theta, so x is equal to small r theta. So this is the relation in between x and theta, so we can put in this formula. So how we can put here x dot is equal to, we can write here r theta dot. So x dot square is equal to r square theta dot square. So we will write here as a half m r square theta dot square. So this is the final formula we can write in terms of theta. Now in the same way, for potential energy we can replace this delta. So now we will consider the point of contact of this spring with disc is A. Now when disc is getting rotated, then because here the spring is getting attached. So here is the new position of this point A dash. Now here also we can find out this deflection delta. So again from A dash I will draw here one perpendicular line, and here on this line O to A, here is the point of contact Q. Now in this triangle OQA dash, so what is this O to A dash? So O to A dash, that is the radius of this outer disc. So here is the deflection delta. Because why this Q to A dash is delta? Because this outer disc is connected to spring, and spring is having deflection delta when this mass m is getting displaced through a distance x. So from this triangle OQA dash we can say that delta is equal to capital R sin theta. Capital R sin theta. So theta is very small, so delta is equal to capital R theta. Now instead of delta we can use here R and theta. So how we can write here? Half K R square theta square. So now how we can use the energy equation, that is total energy U is equal to this translational kinetic energy plus rotational kinetic energy. So I will write here half m r square theta dot square plus half I theta dot square plus potential energy, that is half K r square theta square. So this total energy is equal to constant C. Now we have to simplify this. Total energy U as well as angular displacement theta are variables, and these varies with respect to time t. So we can differentiate this equation with respect to time t. So how we can write? So we will write du by dt is equal to. Now if we observe the first term, then half mr square is constant term. So we will keep as it is, and theta dot square, that is 2 theta dot theta double dot plus. In second term half I is constant term, and for theta dot square we will write 2 theta dot into theta double dot plus half kr square is constant term, and for theta square we will write 2 theta into theta dot, and is equal to constant. So constant is having differentiation is 0. So on the right hand side we will write here as a 0. Now if we simplify this, then this half and 2 is getting cancelled. And here in each term theta dot is the common term. So we will take outside the bracket and we will transfer to the right hand side, so it will become 0. So how we can write mr square theta double dot plus I theta double dot plus kr square theta is equal to 0. So again we will take theta double dot as a common term. So mr square plus I theta double dot plus kr square theta is equal to 0. So here coefficient of theta double dot is this bracket. So we will divide on both sides with this bracket. So theta double dot plus kr square by mr square plus I bracket complete theta is equal to 0. Now we will equate this equation with x double dot plus omega n square x is equal to 0. So x double dot theta double dot equivalent, x theta equivalent. So we can write omega n is equal to under root of this bracket. So square root of kr square divided by mr square plus I. Now we have to find out the natural frequency. So natural frequency Fn is equal to omega n by 2 pi. So we will write here Fn is equal to 1 by 2 pi under root of the term.